All right, so we have to continue with states of matter. Specifically, we have to continue with our solid state. So let's go ahead and start with that. So we were talking about the ionic compound. That's what we did in last class. And in the last class, we talked about the properties of ionic compound. We discussed that ionic compounds are able to conduct electricity when they are in either a solution state or they are in a molten state. Your ionic compounds, okay, when we talk about ionic compounds, they usually have a hard surface, which means you need to apply some force to be able to scratch their surface. And talking about their strength, so when it comes to strength, they are extremely brittle, and the reason they're extremely brittle is because whenever you're applying a force, or you're hammering them into shape, or you apply any kind of force at all, the layers can slide over each other. But when they do slide over each other, basically what happens is that the similar charges or like charges end up coming on top of each other, which creates repulsion, and it causes the layers to literally split apart. Like you can write down that the layers will split apart. So it ends up breaking whenever you're going to apply forces. So those are some of the certain properties that are related to your ionic compounds. Now, when we are talking about our solids, in our solids, we need to know about ionic state, metallic state, and we need to go over covalent compounds. So metallic state, let's quickly go over it since we already have a very good idea of what metallic forces are. Can somebody tell me what are the properties of metallic compounds?
They're shiny.
Yeah, they're shiny, exactly. And
They conduct electricity when solid.
yeah, they can conduct electricity when they're solid as well. What else?
They're malleable and ductile.
They're malleable and ductile. And why are they malleable and ductile? What about them makes them malleable and ductile?
Because the layers can slide over each other.
Yeah, the layers can slide over each other. So when you talk about, okay, first of all, we know in a metallic structure, we have metallic bonding, right? Metallic bonding is what? Metallic bonding is the electrostatic force of attraction between your positively charged ion and the delocalized electron. So the force of attraction you have between the positive ion and the delocalized electron is your metallic bonding. Now, whenever you're going to apply a force to any metal, what's going to happen? The layers are going to slide over each other. Now, in the ionic compound, the layers were also sliding, but what was happening? That same charges would end up on top of each other, which creates repulsion and causes it to break down. In metallic compound, what will happen? Let's say that this layer went forward, right? Like this. Now, you can say, okay, ma'am, so how come, we don't have positive on top of positive or negative on top of negative? Why are we not getting any repulsion over here? This is because your electrons are free to move. So what will happen? Let's say that the layer slides forward and positive is now on top of positive. What will happen since the electrons are free to move, they can come between these two positive charges and they can create a force of attraction instead of repulsion. So that is why even though the layers are sliding in ionic compounds, since the charges are in their fixed positions, it creates repulsion. But in metallic compounds, if same charges will end up on top of each other, the fact that electrons are able to move means that they can move around to adjust in such a way that the force of repulsion is not formed. So that is why your metallic structures are malleable and ductile. Malleable means that you can hammer them into shape, and ductile means that you can draw them into wires. Other than that, they're good conductors of electricity. They are going to be good conductors of heat. They are generally shiny. They are extremely strong. And then when we're talking about their hardness, so hardness is going to depend upon what metal it is, right? Whether you're dealing with group 1 or group 2. So for example, if you're talking about group 1 metals are generally very soft. You can like cut them with a knife. And group 1 metals are generally pretty reactive as well. They tarnish very quickly. So those properties are going to vary depending upon what metal you're dealing with, but generally they are pretty strong. They're malleable and they're ductile, and they're good conductors of heat and electricity. They're going to be shiny, as well as that they are going to usually have high melting point and boiling points as well. So that is all you need to know about the metallic structure. Now, before we move on, we need to discuss alloys. What are alloys?
A mixture of a metal and another
Yeah,
metal or a non-metal, it depends. But like
yeah,
mixed metals, I
yeah.
guess.
It's a mixture of two or more metals or a mixture of metal with a non-metal. And when we talk about it, what is the advantage that alloys give you over normal metals?
They're more
Um,
resistant to corrosion.
Sorry, can you repeat?
They're more resistant to corrosion and they're like stronger
Yeah, they're definitely okay. Corrosion is one thing that's a bit separate, but they're stronger. Why are they stronger than normal metals?
because they
yeah,
have
you can
like
go.
different sized
Yeah,
atoms. They're like
exactly.
harder to break.
Exactly. So they have different size metals. So what's normally going to happen is that since when you're going to, for example, you are applying force on a piece of metal. So generally the layers are going to slide over each other because all of them have similar sizes and they have a regular arrangement. But in an alloy, you have molecules or you have atoms of different sizes. And the atoms of different sizes give it a bit more irregular arrangement and they don't allow the layers to slide over each other as easily as you would have in a pure metal, which is why generally your alloys are going to be much stronger. Okay, so now let's go ahead and start with actually the main thing that in the solid compound that is,
Does this affect
yeah,
like how malleable or ductile they are?
yeah, of course. You are going to have to apply more force then to, for example, if you have an alloy, so if you want to make a sword out of it, you would have to apply more force. Or if you want to make a wire out of it, you would have to apply more force as compared with the pure metal. Okay, let's talk about covalent bonding, covalent compounds. Now, covalent compounds is where your actual detail comes in this topic. When we talk about covalent compounds, you need to know about two types of covalent compounds. You need to know about simple covalent compounds or simple molecular bonding, and you need to know about your um, giant covalent structure. Now, in simple covalent structure, these are generally found in liquids and gases. Liquids and gases have simple molecular bonding, and they're generally not solid compounds. Solid compounds are generally your giant covalent compounds. So let's quickly go over simple molecular compounds. Simple molecular compounds are basically when you have your two atoms that are joined together by a strong covalent bond. And so when the two atoms are joining together with a covalent bond, they're making a molecule. And the forces you have between the molecules are your intermolecular forces. We have done this in quite a lot of detail, so we don't need to go into details of it. You already know that intermolecular forces are really weak, so they are easy to break, which is why simple molecular structures usually have low melting points and boiling points because you don't need to have a lot of um, energy to basically break them. So they are going to be gases or liquids. The reason they are gases or liquids are forced because they have weak intermolecular forces. So they are not going to have that tight regular arrangement. So they're not going to be in solid state. But when we talk about giant covalent structure, that is where the solid state comes in, and that is where you and I actually have to look into it. So in giant covalent structure, one is of course diamond. What do we know about diamond? What properties do we know about diamond, and what do we know about the structure of diamond?
It's like hexagon. Oh,
It's not.
right.
Tetrahedral? I'm not
Yeah,
sure.
it's tetrahedral because you have each carbon is connected or it has a covalent bond with four other carbons, right? So you have, for example, this is your one carbon. We know carbon has 4 electrons in the outer shell, so it can make bond with 4 carbons. So this gives it a tetrahedral shape, right? So it has a tetrahedral arrangement. Every carbon is going to have a covalent bond with another carbon. What else? What else do we know?
What else is like a part of the diamond structure?
Yeah, what else do we know generally about the structure of diamond or even properties, whatever you know?
Oh, diamond's really, really hard because of the very strong covalent bonds between its
Exactly,
atoms. I mean, the
exactly,
carbon atoms.
exactly. So when you're talking about diamond has only covalent bonds. It does not have any intermolecular forces. Because it doesn't have any molecules. It only has carbon atoms. That's it. And those carbon atoms are joined together using your covalent bond. Since it only has covalent bonds present, so it generally has really, really high strength. It will have a high boiling point and a melting point because you need a huge amount of energy to be able to break these covalent bonds. Okay, let me go ahead and ask you something else. So when we are talking about our giant covalent structure and we are talking about molecules, simple molecular structure. So one of the differences that giant covalent structure only has the covalent bond and simple molecular only has, it has both covalent and intermolecular forces. Can you think of any other difference between the two of them? For example, if I give you any unknown structure, how would you be able to tell if it's going to be a giant covalent structure or a simple molecular structure?
The shape.
Not exactly. Even if you have a simple molecular structure and you have hydrogen bonding or you have dipole-dipole interactions or you have lone pairs, you're going to end up in different shapes. So how is that going to give you an idea? Because the shape is going to depend upon the number of lone pairs, your electron repulsion pair theory. That is what it depends upon, not on what type of bonding is present. Any idea?
So by melting or boiling point.
That's one way you can know by melting or boiling point. But okay, so but what I have just given you a structure, or I've just given you the formula, for example. Now, how are you? The melting point and boiling point is not given to you. How are you going to determine it?
The melting point of carbon, I mean of diamond.
If the melting point or boiling point is not given to you, then how are you going to determine it?
Since it's a pure substance, I mean, even though it sounds, I mean, might be impractical, but
In an exam they've given you, you can't get any other information. They haven't given you melting point or boiling point. How can you, at the moment you need to guess what kind of structure it has?
oh, because it's solid.
Yeah, you can go ahead and say it is solid, that's fine. But the easy way, okay, the easy difference between the two of them is that in a molecule, the number of atoms are fixed. For example, H2O. Hydrogen will always be 2, oxygen will always be 1, right? For
Yeah.
example, when you if in your I3 you must have studied about fluorine, which was C60. It has a formula C60. It doesn't have any other atoms. The only atom it has is carbon, but it has number 60. In each molecule there are 60 carbon, so the number of atoms inside it are limited, as opposed to a giant covalent structure like diamond, where the number of carbons can be anything at all. There is no requirement, there is no limit. All that depends upon is bigger the diamond, the more carbons it is going to have, as opposed to C60. C60, each molecule can only have 60 carbons. That is it. So that is a prime difference between a covalent, giant covalent structure and a simple molecular structure. In a simple molecular structure, the number of atoms are going to be 50. Have carbons. You can only have 2 hydrogen and 1 oxygen. That's it. In a giant covalent structure, you can have any number of atoms as the depending upon the size. There is no limit to it. So that is another thing that diamond has. Any number of carbons can be present. There is no limit to it. There's no formula C4, C8, C6, nothing. Any number of carbons can be present. It all that depends upon is how big the diamond is. That is it. We already discussed that diamonds have high melting point and boiling point. Can you think of any other properties of diamond?
It doesn't conduct electricity.
It doesn't conduct electricity. Very good. Why doesn't it conduct electricity?
Doesn't have any delocalized electrons.
It doesn't have any delocalized electron. It's a giant covalent structure. It will not have any delocalized electrons. So you are not going to be able to conduct electricity, right? And we already discussed that it has a lot of strength. It is extremely hard, which is why often, when you have your drills that are used to, in your rocks or in your mining, a lot of the drills that you use, they are actually coated with diamonds. Because diamonds are so hard that they're able to cut through rock. So that is the properties of diamond. Now, before we continue on to our next one, which is graphite, does anybody know what an allotrope is?
Yeah, isn't it like the same like suppose same element but like different forms of it?
Exactly. It's the different form of the same element. For example, diamond and graphite, they're both made of carbon. But graphite is in a different structure, diamond is in a different structure. But they both have carbon inside of it. So diamond and graphite are allotropes of each other. So that brings us to the structure of graphite. What do we know about the structure of graphite?
It's hexagon.
Yeah, okay, fine. And it is the carbon atoms are arranged in hexagons. That's completely correct. And what do we know?
Electricity.
Each carbon is bonded to three other carbons, so they are
Yeah,
delocalized electrons.
exactly. So when you're talking about it, your graphite, okay, so first of all, it has an hexagonal shape, completely correct. Each carbon is going to be connected to three other carbons, that is completely correct. Now, each, your hexagonal arrangement is going to be in layers. So you're going to have one hexagonal layer and then another hexagonal layer and then another hexagonal layer. And each carbon is binding to three carbons. So that is why you have your delocalized electron, because carbon has 4 electrons in the outer shell. So three of them are being used to make a covalent bond. So the fourth one is going to allow you to have that delocalization. It's going to let you have that free electron, which is why it is going to be able to conduct electricity. We know that graphite can conduct electricity, that is why. And you are going to have this hexagonal layer, hexagonal structure, and it's going to be arranged in layers. Now, what do we know about the properties of graphite?
It conducts electricity when solid.
Yeah, it conducts electricity when solid because it has free electrons. What else?
It acts like a lubricant.
Yeah, why? Why? How is it able to act like a
Because
lubricant?
it has it like between each layer of
Yeah,
like graphite, it has very weak van der Waals forces of attraction, so they can slip and slide over each other.
yeah, exactly. So between the layers,
What?
you have got okay, so this is one layer of your graphite, okay? And this is another layer of graphite. Now, between the two layers, you have your van der Waals forces, right? So what is going to happen is that because you have these van der Waals forces between the two layers, so the layers are able to slide over each other. That is why, so you have graphite in your pencil, right? When you write with the pencil, what happens? It wears off. The tip of the pencil gets smaller and smaller. How does that happen? Because it has a layered structure and you have van der Waals forces between the layers. Since you have van der Waals forces between the layers, what is going to happen? The layers are going to be able to slide over each other easily. That is why graphite is generally a soft material. It's not hard. It is able to slide over each other. That is why you can use it in your pencil. That is why you can often use it as a lubricant as well, because the layers can simply slide over each other. Is that making sense?
Yes.
As well as that making sense?
Yeah.
Okay. So graphite also has a high melting and boiling point for the same reason as your as your diamond, right? Because when you are trying to break graphite, you're not just trying to separate the layers. Separating the layers will do you no good. You need to break the carbon-carbon bond. You need to break the covalent bond. And that needs a very large amount of energy. And that is why they will have a high melting and a high melting boiling point. Now that is graphite, we need to come to fluorine. Fluorine is C60 and fluorine. Okay, so first of all, what do you guys think? Fluorine is going to be a giant covalent structure or a simple molecular structure?
This is carbon.
Yeah, carbon 60, fluorine. What is the big difference?
I think it's probably wait, isn't this like some nano structure or
No,
something? I forgot the
no, no.
name.
This is not nanocarbon. No,
Oh, okay, never mind. Okay.
this is allotrope of carbon. Okay, it's called C60 and the name is fluorine. Now, how do you, is it a giant structure or?
Is it like limited to how many atoms it can
Yes,
have?
exactly. So the number is given to you, it says C60. So each Molecule can only have 60 carbons. So since we have a limited number of atoms, we can't exceed 60. That means that this is a simple molecular structure, not a giant covalent structure. Okay? And when you are going to talk about it, so this is, for example, this is one molecule. It has got 60 carbons. This is another molecule. It has got 60 carbons. This is
So it's
another
basically a
molecule.
simple molecule, right? I mean, a
Yeah,
simple.
simple molecular structure. Exactly, like H2O, like nitrogen gas, like hydrogen gas. It is a simple molecular structure. So you have, this is one molecule of carbon, which has like 60 carbons in it. This is another molecule of carbon, which has 60 carbons in it. And between them, you have intermolecular forces. Now, it will have low melting point and it will have low boiling point as well. Why? Because once again, you need to break just the intermolecular forces. You don't need to break anything else. That is why you don't need, that you don't need to have that high of an energy, or you don't need to have that much of an energy. So that is one thing. Now, another property of fluorine is that it cannot conduct electricity. Now, this is my question to you. When you talk about fluorine, the structure is C60, and in fluorine, every carbon it binds to three carbons, just like in graphite. There were every carbon binds to three other carbons, right? The same is true for over here. Every carbon binds to three other carbon. Now, because you can see it has a hexagonal ring structure, just like graphite. So you have a hexagonal ring structure that is giving you the C60 molecules, and each carbon is bonded to three other carbons. So in graphite, we said that since there are only three bonds, that means that the fourth electron will be free and delocalized. It can conduct electricity. Now, fluorine has the same logic. It also has one free electron that is not involved in bonding. So that is also free and delocalized. Why is it that graphite can conduct electricity, but fluorine cannot?
Is it because perhaps in fluorine they have like dative bonds between like the free electrons, or
No,
no?
no, there are no dative bonds. The requirement for a dative bond is what? What are requirements to have a dative bond?
Oh, right. It's a positive. It's an electron deficient ion.
Electron deficient ion and a lone pair of electrons.
And a lone pair electron. Yeah.
So you have neither. So why
Yeah.
is it both have free delocalized electrons? Why is it that graphite cannot, but C60 can? Graphite can conduct electricity, but C60 cannot.
Is it because C60 has like a circular structure, like spherical structure, I mean, sorry. So like the
Mm,
delocalized electrons can't move necessarily, even though they're delocalized. I'm not sure.
okay, you are close to the answer. Basically, the reason is because in graphite, the delocalized electrons can move between the layers, right? They can move between from one layer to another. In C60, the delocalized electrons can only move inside the molecule. They can't move between the molecules. It can't go from here to here. It can only stay within the molecule. So that is why even though the free electrons are present, they don't have the mobility to cross from one molecule into another. They can only move within one molecule. That is why C60 cannot conduct electricity, but graphite can, because in graphite, the electrons can move from one layer to another. So that is why your C60 fluorine does not conduct electricity, because the fourth electron on each atom can only move within the C60 molecule. They cannot go from one molecule to another because it's a molecule, right? In graphite, it's not a molecule. You just have atoms. That's it. You have carbon atoms bonded to each other and you have layers. There are no molecules. There are no molecules in graphite. You just have carbon atoms. So the electrons are free to go from one atom to another, one layer to another. But now this is a molecule. Since it's a molecule, the electron has to stay within the molecule. Even if it's free, it has to stay within the molecule. That is why C60 cannot conduct electricity, but graphite can. Making sense?
Yeah.
And the last property of C60 is that it is not as hard as diamond, and you already know why. Because it does have intermolecular forces of attraction, they are weak, so it's not very strong. So that is what you need to know about C60. Now, we have something known as silicon oxide. What do we know about silicon oxide?
It does not conduct electricity.
Okay, and it does not conduct electricity because it does not have any free electrons. Fine.
Each oxygen atom is bonded to two silicon atoms.
Yeah, each silicon atom is bonded to four, not to four oxygen atoms.
Oh no, I said
This
each oxygen is bonded to two.
Okay, okay. Each oxygen is bonded to two silicon atoms. That's fine. That's correct. Each silicon is going to be bonded to four oxygen atoms. And the
Right.
formula for silicon oxide is silicon 4 oxide, or if you write it down, it will become SiO2. And we know silicon oxide has properties similar to diamond, which means it's going to have high melting points, it's going to have boiling points, and it's not going to conduct electricity. And when you talk about where you can find silicon oxide, you can find silicon oxide
In
in
sand.
exactly in your sand or in your quartz crystal. Your quartz crystal also have silicon oxide in it. Now we start talking about our carbon nanoparticles, right? So when we're talking about carbon nanoparticles, what are carbon nanoparticles? Any idea?
I've heard of them, but I'm not sure. Like, is
Okay.
graphene nanoparticle, by the way? Just asking.
Uh, Yeah, not exactly. Graphene is just like if you take just one layer of graphite, that's
Right,
it.
yeah. That's
Just
graphene.
yeah, just one layer of graphite is going to be your graphene. So not exactly. You can't exactly say that. Okay, nanoparticles. Yeah,
It's small.
yeah. Basically, it's the size that is important, right? So when you're talking about this it is an allotrope of carbon. That means it's another form of carbon, but when it comes to size of the particles, the particle size are very small. They are like 10 raised to power negative 9, which is nano. So that is why we call them nanoparticles, because the size of the particle in its of itself is really small. And when we are talking about the properties of your nanoparticles, what are the properties of nanoparticles? So we can go ahead and take a look at that. So first of all, so nanoparticles are just the same as carbon. They're just like an allotrope of carbon. That's it. There's nothing specifically out there about them. The only main difference that they have is that they are basically going to um, have your really small tiny particles that are going to come under your uh, nanoparticles. When we talked about fluorine over here, fluorine is also considered to be, by the way, carbon nanoparticles. This is also considered to be a carbon nanoparticle. And another type of carbon nanoparticles that we have are basically your nanotubes. So in carbon nanoparticles, you have two. You have your fluorine and you have your nanoparticles, or you have your nanotubes. Now, by the way, in fluorine, there are different types of fluorine. Okay. The full name of fluorine is Buckminster fluorine.
Miss,
Buck, yeah.
where do they get, like, is it just natural for the carbon to somehow be really small?
Yeah, it is
How does that
natural.
work?
Yeah, it's natural. It's natural. They're naturally found. And the full name of fluorine is Buckminster fluorine, and there are different types of it. So, for example, you can have C60, you can have C120, you can have C20, C70. So, there are different types of Buckminster fluorine. C60 is the common one, but you can have other types as well, but they will all have similar properties. So, you don't need to worry about that. They will all have same properties.
Do we need
So,
to know the use of it? Like C64, like does it have any use in our daily lives or
no,
something?
yeah, okay. So no, it's used in your you don't when you're talking about it. So your fluorine has, I will come to it. I'll come on to different uses that fluorine has. You just need to know a few of them. You don't need to go into details of any of them. You just have to, I have an idea of a couple of them. That's it.
Oh, okay.
Okay. So one of the, we have done C60. Another type of fluorine is your nanotubes, that is over here. Now, when we talks about nano, okay, by the way, nanotypes are another type of fluorine. Fluorine was basically what was your T60. That's why I was being specific. T60 fluorine, because you can have different types of fluorine. So in your nanoparticles, you have C60 fluorine, and then you can have nanotubes, which is just another type of fluorine. And nanotubes are fluorines of hexagonally arranged carbon atoms. So you have, see, this, they are all hexagonally arranged, and they have just a single layer that is bent to form a cylinder or to form a tube. So you literally have this one layer of your carbon atoms. The carbon atoms are arranged hexagonically. They have an hexagonal arrangement. They are arranged in a cylindrical structure, and there's just one single layer of them. That is it. And when we talk about the properties of it, so they have high electrical conductivity. The reason they have high electrical conductivity is because you just have one layer. Since you only have one layer, and this is not a simple molecular structure, there is no a number of carbons, right? There's just atoms of carbons. You don't have any molecules present. That is why, since the electrons are delocalized and it's present in just one single layer, the electrons are able to move from atom to atom, and it is going to have high electrical conductivity. They also have high tensile strength, right? Because they have a lot of strong covalent bonds, and the presence of strong covalent bonds allows them to have a very high tensile strength, and they have high um, very high melting point as well, because of course you only have carbon bonds, you don't have any intermolecular forces, so you need a lot of force to be able to break them. So these are general properties that we have already discussed. Yeah.
Wait, I don't understand. You
Mm-hmm.
said that fluorine doesn't conduct electricity. If this is the
So
type
yeah,
of
this is
why?
there. This was a specific. See, I was throughout. I was saying C60 fluorine, right? I am being specific about which type of fluorine. So this type of fluorine had a simple molecular structure, which is why it was not able to conduct electricity. When this is just another type of fluorine. So in this type of fluorine, you don't have a simple molecular structure. You don't have a limited number of atoms, right? It can be any number of atoms at all, which is why over here you were having the conduction of electricity because of delocalized electrons. This is different type. Being fluorine doesn't mean, when I say fluorine, it doesn't mean that you instantly have a simple molecular structure. There are different types. So the C60 type was a simple molecular type. This is another type. This is a giant covalent type, or this is a nanotube type. It's different types. When I say fluorine, I do not mean at all that it's just one thing. You can have different types of it. So C60 is just the type that has a simple molecular structure. Is that making sense?
Yeah.
Okay, so that is what you have about your carbon nanoparticles. In your carbon nanoparticles, you have your fluorine. And when you're talking about your fluorine, we have the C60 type, and then we have this type, that is your nanotube. Now, when we are talking about,
I'm so
yeah.
sorry. One question about carbon.
Mm-hmm,
You said that they occur naturally, right? So, like,
mm-hmm.
how do we get access to them since they're so small? Like, yeah.
Obviously, okay. So when you are talking about them being so small, the size of the particle is small. But when they're going to come together, they're going to be making a bigger structure. Think about it this way: that you have your diamond. You
Yeah,
talk
no,
about
that makes a lot of sense. Yeah, obviously. Oh, so we
yeah,
make it big though, right? We like
yeah,
we
exactly, because there's so much of it present that it is of course going to be, when I say it is so small, I mean the particle or the size inside of it is small on an atomic level, not that
oh,
overall it is a small, like, if you look at diamond, if you look at the carbon inside a single atom, that's going to be extremely small, but multiple of them are
yeah,
coming together to give you a
yeah.
huge structure. So that is the same thing over here. Okay, so we have, when we
Can
talk
you make
about
them in a lab?
yeah, sorry, can you repeat it?
Can you make them in a lab?
You can make them in a lab. I mean, you can try to make them in a lab, yes, but normally for stuff like this, you need to have like, I mean, people are working on it. They are working with nanoparticles. It has got a lot of uses. But generally, you can make it in a lab, but you need to have the right equipment, you need to have the right substance, and you need to, it's a very technique sensitive thing. But
Right.
it is something that a lot of people are working on. Nanoparticles are like a really in thing these days, and a lot of people are working on it, and they're trying to use it to make different kind of structures or new structures, or come up with cheap and alternative way to make structures that we already have. Okay, so let's go over the uses of fluorines, where you can go ahead and use your fluorines, right? So first of all, you can use it to make something that's known as metal complexes, right? You can use it to make metal complexes, and metal complexes, you don't need to worry about it. That is something that we're going to go ahead and we're going to do it later on as well. But let me give you guys an idea of what metal complexes are. So metal complexes, okay. When metal complexes, basically you have this central metal atom. For example, you have an atom of metal that is located at the center, and that central atom is then located or is then surrounded by other ions, or it is surrounded by other molecules. Have you guys heard of the term ligands? Have you gone over ligands before?
Could you repeat the term? Sorry.
Ligands. Have you guys done? If you haven't done it, we have it in the syllabus
No,
anyways.
I
We will
don't
do it.
think so.
You
Yeah, I
guys
haven't
haven't
done it,
done.
but I've heard of it many times.
Yeah, okay. Then I'm not going to get into it because we have to cover it later on anyway. So it's going to take too much
Was
time
this
and
in
we'll
the
get.
IG?
I don't think you guys probably haven't done it in IG. Okay. So
Yeah,
you
I
can,
looked over it.
yeah. So I'll right now just tell you what a metal complex is, and we're not going to get in detail of it because we do have to cover it later on anyways. So normally what happens is that, for example, you have a metal, for example, cobalt, right? And that cobalt is then surrounded by NH3 on all sides.
Oh wait,
This is
isn't it something? Isn't hemoglobin in our blood like this? Like I
a
don't think.
not exactly. The hemoglobin in your blood is not exactly like this.
Oh,
Okay.
okay.
So you have like a metal complex. A hemoglobin in your blood is iron, and it's normally surrounded by your protein. That is a conjugated protein. We call
Oh
it
no, I mean,
conjugated.
yeah, yeah. No, but I mean that's
A
also a ligand thing, right?
Not exactly
Oh,
ligand.
okay.
Ligand is when you have your metal and it's surrounded by, I guess you can go ahead and say that, but not exactly. Ligand, I will explain to you guys
Oh,
what ligand is when we get into it. I'm not getting right now because it's going to get too much. But this is what an example of a metal complex is. You have a metal at the center, an atom of metal, and then it is surrounded by other ions or other compounds, right? So this is your carbon at the, sorry, cobalt at the center, and it is surrounded by an ammonia. So this is an example of a metal complex. So that is one of the uses of your carbon nanoparticles, or one of the uses of fluorine, that you can use it to make metal complexes, right? You can attach other reactive groups because they have a free electron. You can attach other reactive groups like ammonia, like other groups, hydroxide, any other group. You can go ahead and attach it to them. Do you have that so you can use it to attach other groups. If you want to attach other groups and make up a new compound, you can do that. You can use it to make your metal complexes. And when you talk about, for example, Buckminster fluorine, which is C60 fluorine, if I talk about it specifically, you can even use it to, trap small molecules or atoms inside of it. So you want to be able to trap a molecule or an atom specifically when it comes to medicine, right? So we need a vehicle, something to be able to deliver the drug to the target organ or whatever organ we want to get the drug to. So we want to get the drug over there. So in that situation, we can use something like fluorine, where we can put the drug inside and then we can give fluorine inside of it. Your nanotubes can be used as in electrical circuits. You can use these nanotubes to make electrodes and make really, really small batteries because it's in a smaller size, right? You can use these nanoparticles into clothing, into sports equipment, to give them more kind of strength. So those are all the uses that you have of your carbon nanoparticles. Then finally, we have graphene. What is graphene? Graphene is just a single isolated layer of graphite. Like if I just take one layer of graphite, that's it. Yeah, was anybody saying anything?
Yeah, I asked if you could like re-explain the thing with the complexes because I didn't
Okay.
understand.
No, I'll tell you. Metal complex, don't worry about it too much. You have to do it later anyways. It's in your chemistry syllabus somewhere. I'll see whether it's AS or A levels, but it's there. You have to study it. So don't worry about it. Just get the very basic concept. A metal complex is when you have a metal and it is surrounded by other ions or other compounds. So for
Also,
example, yeah.
asking you metal complexes, but it's not covalent or ionic bonds, right? These are like, are these those sort of bonds, or are these like a different sort of bond?
No, the type of bond is going to depend upon mostly its covalent bond, but the type of bond is going to depend upon what is involved in the metal complex, right? Is
Oh,
it
okay.
a metal binding with a metal ion? Is it a metal binding with a non-metal ion? That is the type of bonding is going to be decided by what is involved in the metal complex. Or you
Oh,
have to
so it could be metallic or covalent.
Yeah. So all you have to understand is that in a metal complex, the central atom, the atom at the middle, is a metal, and that metal atom is surrounded by other compounds or other ions. That's it. This is one example. You have cobalt, that is a metal, and it is surrounded by ammonia. That is just one example. This is what a metal complex is. It's literally in the name, metal complex. So you're making a complex, which means you're making a combination. So the central, at the very center, you're going to have your metal, and that is going to be surrounded by any other ion or any other compound. That is all you guys need to understand for now. Okay. When we get to it, we're going to be doing this in detail anyways. Is this clear? So is this more clear now?
Yeah, okay.
Okay. So this is basically what your metal complex is. And you can use these fluorine to make these metal complexes. Okay, so now we're going to go over graphene. Graphene is literally just one layer of graphite. If I just go ahead and take one layer of graphite, that is going to be your graphene. That is it. And when we are talking about our graphene, your carbon atoms are going to be hexagonally arranged. And when we talk about it, so graphene is not rigid, and you can easily, it has got flexibility into it simply because it's not arranged in layers. You have just one single layer, so it's a bit flexible. It's not completely rigid. And what other properties of graphene are there? Graphene is the most chemically reactive form of carbon. So out of all the forms of carbon, um, fluorine, nanotubes, your graphite, all of the forms of carbon, graphene is the most chemically reactive. Simply being because it's a single layer. It's a single layer, the surface area is high, you can have fast chemical reaction. Single sheet of graphene also burn at low temperatures and they are more reactive. Graphene is extremely strong for its mass. That meaning, what do I mean by that? If you look at the mass of it, right? So compared to the mass, you would say, okay, that's a very small mass, so it can't be that strong. We don't have much of it. But if you compare it relatively to the mass, like in small masses, graphene is very strong. And why is it strong? Because it has the strong covalent bonds. So they allow it to have that strength. And graphene will conduct electricity and heat much better than graphite. Once again, you have a single layer. There are no intermolecular forces. The graphene will be able to, so the delocalized electrons are able to move much faster because, they only have to travel within one layer. They don't have to travel from one layer to another and then another, then another. They have to travel through only a single layer, so they'll be able to travel faster. That is why it can conduct electricity and heat much better than graphite. Making sense?
Yeah, okay.
Yes, it makes
Are you,
sense.
gu- are you guys sure? Anything you want me to go over? Any part at all? All good?
Yeah, all good.
All right. So we are done with our topic of um states of matter. Okay. One thing that is left and that I'm not going over with you is that the last thing you need to know is conserving materials, which is just you need to go over why we need to conserve material and what are the reasons for it, right? So I want you guys to go over that part, and in the next class, we're just going to discuss whatever you guys have gone over it. Okay, it's in the book. You guys can go over it on your book, and we're going to hold a discussion on it. And you guys are going to give me an idea of what you have studied. It's pretty small, and pretty everything about it is pretty much common sense.
Oh, okay.
Okay,
hold on. Let's go ahead and do a few questions related to the topic.
Miss,
Yeah.
I have to go to the airport right now. So is it fine
Okay.
if I
Yeah. Go on. You can go. No
thank you,
problem.
Miss?
Okay. Have a good day. Bye, Zoya.
We can also
Yeah.
just end the class now if you like. That's fine, like with me.
Okay. If that's okay with you, then we can go ahead and we can end it over here, and we can then we'll start with the past papers in the next class. Then, if that's okay with you.
Yeah, that's fine with me. Okay, thank you,
All right.
ma'am.
All right. Thank you, Devancha. See you next time. Bye.
See you next time. Bye.